All right, let's finish off lesson 2.3 with these examples. These are two of the three examples that we did in lesson 2.2, but now we're going to take a look at them as a numeric pattern as opposed to a visual. So let's take a look at the first one, which I think was the second example from lesson 2.2. Again, what we're going to do is we're going to find the rule for the nth term, meaning the number of squares in the figure. So I think that would be a good thing to define. So what we're going to do is we're going to find a numeric pattern. I'm going to kind of turn this into a table where, again, this is my n and this is my value. My value meaning the number of squares. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. And let's see if you want, you can look back at your notes from lesson 2.2 and record the number of squares in figure 4 and 5. Let's see if we can find a constant difference. So to go from 4 to 6, I add 2. To go from 6 to 8, I add 2. And so it looks like our constant difference is 2. And so then for our nth rule, so for our nth term, the rule is going to be 2 times n plus something. So now again, we need to get that plus something. To do that, I'm going to focus on the second term, which has a value of 2. So then I would do 2 times 2, because it's n equals 2, plus something is going to equal 6, because that is the value of that term. So 4 plus something equals 6. This time I'm going to do my math correctly. The something equals 2. And so this nth term would have a value, would have a rule of 2n plus 2. Let's double check and make sure that works. So if n is 3, 2 times 3 plus 2 is 6 plus 2, which is 8. And that is what I have here. Here's a couple other ways to look at this, and this is something, if we were together in class, I would kind of ask you to generate some ideas. Is there a couple ways we can look at this? So I'm just going to tell you one of the ways we can think about this. What if we kind of box this out for a second? And I want you to notice that this has a length of 3 and a height of 2. And so if we were going to find the area, we would do 2 times 3, or 3 times 2. Same thing with this one. I would do 2 times 2, and here I would do 2 times 1. And I want you to notice that the second number that you're multiplying by to find the area is always that n value. And the first number is always 2 because we have 2 stacks of blocks. So that's another way to look at where this 2n is coming from. And then where's this additional plus 2 coming from? Well, as we can see, we have 2 extra squares on each of the sides. You could also set this up as a bit of a difference if you wanted to make this a larger square and then do a subtraction problem. Like you could make something instead of, I think that's a little bit harder, but it's another way to look at it. Like if you thought about this as something larger and then you kind of subtracted out these 2 pieces here, you would still end up with 2n plus 2 as long as you algebraically set it up correctly and did some distributing. But just a fun way to look at it. And I think it's just neat that we can approach things from a visual perspective, from a numeric pattern, and then kind of tie those 2 things together. For the second one, again, we're taking a look at the number of squares in the figure. So you might want to pause the video maybe and try this. So when n is 1, there are 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. When n is 2, I'm sorry about my phone going off. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Again, let's look for that constant difference. And I'm seeing that 8 plus 4 is 12. 12 plus 4 is 16. So that is going to be my constant difference. And so for my nth term, I'm going to have 4n and then plus something. So what is that something? This time let's pick the third term and value. So 4 times 3 plus what is 16? 12 plus what is 16? The blank is 4. So this term has an n, excuse me, this sequence or pattern has a 4n plus 4 nth term value. Now this is kind of interesting. Both of these ended up with the constant difference and the constant. So the number we were multiplying by the variable by the n, as well as the number we were adding, ended up being the same. That is not always true, but it just happened to be here. So again, we could look at this in much the same way we did that first one. If I looked at, there are 1, 2, 3, 4 chunks of 3, and then there are an additional 4 squares on the side to add. So that's another way that 4n plus 4 comes in. You could also set this up as a multiplication problem and do a subtraction. You would have to actually set up some foiling, which is kind of neat. If we did a big square here, this, for example, has a side length of n plus 2. And I'm saying that because my n value is here, 1, 2, 3. So my term is 3, and then I have 2 extras on the side. So this has a length of n plus 2, and it also has a height of n plus 2. So to get the area, which would be the number of squares, I would do n plus 2 squared 4 times n plus 2. But then I'm missing a piece. And what I'm actually missing is something that's n by n, or something that's worth n squared. So I'm subtracting n squared. So if I were to FOIL out n plus 2 times n plus 2, this would actually get me the perfect square trinomial, n squared plus 4n plus 4. Or you could just FOIL, but I used a factor pattern. It's a squared plus 2ab plus b squared. But then look at that. The n squareds will inverse each other out to become 0. And so I get 4n plus 4. I just love looking at things in a bunch of different ways. So all this, again, is to set our brain up for noticing and recognizing patterns as we are moving through our curriculum. Because that is one thing I love about this curriculum. It's not me telling you a lot of what's happening geometrically. It's you discovering it and using these inductive reasoning skills. Great job in this lesson.